Hello everyone. Welcome to another lecture of uh, design and analysis of algorithm. And in this lecture, we are going to delve deeper into how to analyze an algorithm and what makes the algorithm best among all the other algorithms for the same problem again. So let's move. Let me start this. Uh, Let me take the black pen. And so, what are the qualities of a good algorithm? So, the main question is, suppose we have a problem and we have to write algorithm for this, and we have, let's say, three students, and all these three students write different algorithm for the same problem. Okay, so sorry, A2 and A3, and these three students have written these three different algorithms. So how can I decide which algorithm to choose? So I have two parameters on which we will basically work. The first parameter which we are going to see is time taken by the algorithm or by the program made by from that algorithm to run in our computer memory, in our RAM, how much time the algorithm is going to take. Suppose this algorithm is going to take 10 seconds, this is taking 12 seconds, and this is taking 14 seconds. So I'm going to choose A1 algorithm because it is taking lesser amount of time. Another parameter which is used to judge the quality of the algorithm is the space taken by the algorithm. How much space algorithm needs to run in the computer? How much space it is going to take in the RAM to run? Okay, so suppose A1 is taking 2 MB to run. This is taking 2.5, and this is taking 3 MB. So again, I'm going to choose A1, and the question now arises: what if A1 is taking more space? Now that is a situational thing. From the top of my head, we are going to take that algorithm which is going to take lesser amount of time. But if the need is to use lesser amount of memory, we are going to take uh, some other algorithm which is taking lesser amount of memory depending on the problem. Okay, so these are the two main parameters. So let me see some. Let's go to some specific definition. So in the time part, the amount of time it takes an algorithm to run as a function of the length of the input is known as the time requirement. The number of operations to be done by the algorithm is indicated by the length of the input. Okay, so how big is the input is also definitely going to uh, determine how much time the algorithm is going to take to run in the computer. And the second is the memory, the amount of memory utilized by the algorithm, including the inputs to execute and create the output, is referred to its memory requirement. Then we have the accuracy. There can be more than one solution to the given problem, but the one which is the most optimal is termed as accurate. Okay, so we have to test it. Okay, I cannot say just by running it on 3 4 inputs we cannot determine it is the best algorithm. We have to run many different types of test cases to check if it is giving us accurate results in different scenarios. So the analysis can be go to one day depending on how small or how big is our problem. If the problem is big, it may go to it may take several months to optimize uh, and to get the required result. Okay, so these are the qualities. Now, how to compare the algorithm? How to say this algorithm is good and this algorithm is bad? The two factors we have already seen, or let us say three factors: time, space, and accuracy. But also we have something called as execution time. Okay, so the topic is to compare algorithm. Let us define few objective measures. It, can it be the execution time? Now, for example, suppose I am running a program. I'm running a program on, let us say, Core i3 machine, and the same program I'm running on Core i7, and the same program I'm running on supercomputer, supercomputer. So definitely a supercomputer is going to give me fast execution time. So can I say that, can I compare it using the execution time? I cannot, because it is not giving me a definite perspective of how it will behave in different machines. Okay, so execution time cannot be an ideal measure. The next point, can the number of statements executed be a correct measure? For example, one coder is writing 10 lines of code to run the same program, and another is writing 5 lines of code to run the same program. So depending on the style of writing, depending on what language you are using, the number of statements are getting increased or decreased. So is that a good measure? Definitely not. Number of statements executed is also not a very good measure. So what is the ideal situation? See, the ideal situation is we need something which is independent of machine use. It should be independent of the machine use, because there can be different machines we are using. Somebody may be using Pentium 4 computer, somebody may be using Core i3, i7, somebody is using it on his mobile. So we need some function, some way, so that it can be it's not it's unanimous. It should be clear what is the running time, or in how much time it is going to run. This independent of the machine. So what we do is, here I have written something called as fn. If we can make a function fn where n is the number of inputs, and this fn is going to be made for all the different algorithms, then we can compare this function fn with all the different algorithms, and then check what is the time complexity, or in how much time it is going to run, what is the quality of the algorithm. Okay, so we will see how to make this fn and how to compare it. Okay, we will see later down this video or in the next video. Now, what are the categorization of complexity? In performance analysis, we have already seen there is something called a space complexity, how much space the algorithm or the program is taking in the computer during execution, and the time complexity, how much time it is taking to get fully executed. Now, when we talk about time complexity, there are two types of uh, time: compile time and run time. Now, a program, we basically, you know, for us, running time is more important than compile time. Why I'm saying is this: one program, if it is compiled successfully, then we don't need to compile it again and again. We can make it a exe and then run. Okay, different instances we can run, but we will compile it just one time. Okay, so if we have compiled it, then that is done, and we move to the running time complexity, depending on how, on different types of input we are getting. We may get smaller input, we may get bigger input. So on that, we will check what is the running time complexity. Okay, the next, okay, is some in space, the space complexity. We have seen the running time complexity as compile time and run time. What kind of different kind of spaces we can talk about? There is something called as auxiliary space, or the temporary space created during the running time of the algorithm or the program. See, what can be a temporary space? The space which is deleted or which is not used after the program is executed. But there is some space used for the input. So we may need to store the input for further use. So in that case, the space used for the input is one space we need, and the auxiliary space is the temporary space we need for certain input. Okay, so moving on. So now there is something called as the components to calculate space required by the algorithm. Space complexity, how to calculate that. Okay, so before going into that, let us see what is something called as fixed part. Now let's see the definition. Fixed part is space for code. This is independent of the input and output. This part includes the instruction space, space for simple variable, space for constant, and so on. Now what does these lines mean? See, let me directly jump to the code. We are talking about fixed part. What is fixed part? See, I have started code here, main, then I have written n is equal to 10, and I have just printed 10. It will just get printed. So the fixed part is n, the value of n is 10. Okay, the value of n is 10 is not going to change. Okay, so n has fixed value that is 10, and size of the integer type data is fixed in memory, 2 for 32-bit compiler and 4 for 64-bit compiler. So we know this is not going to change. This is not dynamic in nature. So what is dynamic in nature? Moving on. So what is the variable part? Again, let me directly go to the code. This is the code, and we are just writing factorial of a number. So depending on the input, what is the input? Determine how much time this program is going to run. Is it or not? If n is 10, let's say we are measuring time in second or nanosecond, whichever you like. So it is going to run at least for 10 seconds. If every operation is taking 1 second, if n is 1000, it may take 1000 seconds. Okay, so memory taken by the algorithm is dependent on the value of n. Here, okay, we are talking about the memory here. I've talked about time also. So the fixed part here, what is the memory here? We know this is a constant amount of variable, and this is taking constant size int it is taking, and in the variable part, depending on the input, the stack size is going to change. Okay, because it is a factorial, the stack will change, the stack size will change. Okay, so depending on the input, we are changing the size. Okay, so this is how we calculate the space complexity as well as the time. Okay, so thank you for watching this lecture. Let's meet in the next lecture.